Hey everyone, today we're going to talk about asymmetrical encryption and RSA. We're going to go through an example of RSA and also experiment with it afterwards. This is the first official meeting of RSA. So let's see what the difference between symmetrical and asymmetrical encryption is. For symmetrical encryption on the left, pretend Bob wants to send a message, "Hello Alice," to Alice. He would use the key A to encrypt this message into the ciphertext. After Alice receives the ciphertext, she uses the same key A to decrypt it into the original message. So this is the what we've been using for the Caesar cipher. One problem with it is the distribution of the key. So for Bob, he wants Alice to know how to decrypt it. So he needs a secure way to give the key to Alice, but this is very challenging. If he sends a person to tell her, it will be really slow. If he texts her or calls her to tell her what the key is, they can be tracked on the internet. So there is this fault for the symmetrical encryption. For the asymmetrical encryption, it basically avoids this situation by using two different keys. So, for example, Alice wants to send a message to Bob. Bob would first need to generate two keys. There's a public key and a secret key, which is also the private key that Bob keeps. He sends the public key to Alice, and then Alice uses the public key to generate the ciphertext. But Bob uses the secret key to find the plaintext again. So this is why it's asymmetrical. It has two different keys. This way, as long as the secret key remains secret and no one knows about it, this would be basically impossible to crack for an outsider. So for the symmetrical encryption, Alice has the message E. She encrypts it using the key E. Alice has a message M. She encrypts it using the key E, and it turns into ciphertext C. Bob receives the ciphertext C, uses the same E but decrypts it using E, and finds M. For the asymmetrical encryption, Alice has the message E. She encrypts it using the public key. Alice has the message M. She encrypts it using the public key E and finds the ciphertext C. But Bob uses the private key D to decrypt the ciphertext C to find M again. So this is why it's asymmetric. Now let's look at the RSA process. RSA is the most popular type of asymmetrical encryption at the moment, and it is really secure. So at first, Alice wants to send a message to Bob, and Bob is getting the two keys ready. In order to get the keys ready, he first finds two prime numbers P and Q. Then he finds the product of P and Q, which is N. And then he finds phi N. This is called the Euler's totient function, and we will talk about it in the future. But for now, phi N equals P minus 1 times Q minus 1. So Bob has done the preparation work, and now he is finding the public key E. The public key E has to meet two requirements. It is an integer between 1 and phi n, and it needs to be coprime with phi n. Coprime means that the two numbers only has one of the same factor, which is 1. So E and phi n only has one factor that is the same, which is 1. Okay. And then if the E can be any integer that meets those two requirements. So after he finds E, Bob needs to find the private key D, and D only has one requirement. D times E divided by phi n has a remainder of 1. So For D, there is an infinite number of possibilities, and Bob just needs to choose one of them. Now that Bob has the public key E and the private key D, he gives N and public key E to Alice. Alice uses the public key to find the ciphertext. The ciphertext is m to the power of E divided by N and is the remainder of that. So m to the power of E divided by N has a remainder of C, and that is the ciphertext that Alice gives to Bob. And then Bob receives the ciphertext, and he uses the private key D to find the plaintext M. So C to the power of D divided by N has a remainder of M. If he does it like this, then the remainder should be the exact same thing as the message that Alice sends, and this is the whole RSA process. So for step 1, Bob finds the prime numbers P and Q. The bigger the prime numbers are, the bigger the N is, and that makes the message hard to crack for outsiders. So in our example, let's say Bob decides P is 53 and Q is 61. But in real life, the numbers would be much bigger. For example, P and Q might look like this, and then N would be this really big number. If it's like this, then it would be really hard to crack, or it would be impossible to crack, because it's really hard to find the prime factors of a big number like this. Step 2, the length of N equals the length of key. So because we decided that P is 53 and Q is 61, N would equal the product of P and Q, which is 3233. And 3233 in binary is 110010100001, which has 12 digits. So this means the key has 12 digits in our example. But in practical applications, the key for RSA encryption is usually 1024 digits in binary. If it's for something important, the key can reach 2048 digits. The third step is finding phi n. If n is the product of P and Q and Q are prime numbers, then phi n equals P minus 1 times Q minus 1. So in our example, n is 3233, P is 53, Q is 61, so phi n equals 52 times 60, which is 3120. And then Bob finds the public key E. So the two conditions are E is in between 1 and phi n, and E and phi n are coprime. And E has to be an integer. So Bob chooses 17 as public key E, because 17 meets those requirements. And it's coprime with 3120, which is phi n. There aren't any possible common factors of 13 and 3120, because 3120 is not a multiple of 13, and 13 is a prime number. So this means that the only factor of 17 is 1 and 17. So because 3120 is not a multiple of 17, they don't have any common factors apart from 1, and that means they're coprime. In practical applications, the public key is usually 65,537 or a bigger prime number. So because the public key is always public, it doesn't matter if everyone knows it. So that means you can choose the same thing every time. And it doesn't have to be a prime number, but if you make it a prime number, it just makes things simpler. But in our example, Bob chooses 17. And then Bob finds private key D by calculating the modular multiplicative inverse of E and phi n. We're gonna talk about this in the future too. So to find it, he can use the extended Euclidean algorithm. There is an infinite value of infinite number of values of d, but d must be a positive integer. So Bob just chooses one of them, and he decides that d will be 2753. Step 6. Bob sends the public key to Alice. The public key is a package of N and E. So he will send 3233, 17 to Alice, and then he keeps the private key to himself. The private key is a package of N and D, so he's gonna keep 3233, 2753. Now Alice has the public key and she can encrypt her message. So Alice has her message, but her message has to be a number. So she can find the Unicode of the symbols of the words in her message and then use the public key to encrypt it. So that's how we turn the message into a string of numbers and then use the numbers to encrypt it. So, summary of our example. Alice wants to deliver a message to Bob. Her message is 3200. Bob tells her that the public key is 3233, 17, but he keeps the private key 3233, 2753 to himself. What is the ciphertext that Alice generates? Here are the things we know. M, which is the message, is 3200. P and Q are 53 and 61. E, which is the public key, is 17. D, which is the private key, is 2753. What will the ciphertext be? So now we can look at the code. Here's the code for the RSA encryption. First, we have two functions. First is the encryption function. It takes in 4 parameters, P, Q, E, and M. P and Q are the two prime numbers, E is the public key, and M is the message. When we run the function, it will calculate N, which is the product of P and Q. Find C, the ciphertext, which is M to the power of E mod N, so divided by N, and find the remainder. The remainder will be C. And then it returns C, which generates the ciphertext. And for the decryption, it uses P, Q, D, and C. So the two prime numbers, D, which is the private key, and C, which is the ciphertext. In the decryption function, it finds N again, which is P times Q, and then finds the M, the message, by finding the remainder of C to the power of D divided by N, and that gives us M, which is the plaintext again. So those are the two functions we use to find the ciphertext or the plaintext. So over here, it's an example of the RSA encryption process. M is the plaintext, C is the ciphertext. There are 3 restraints. D has to be greater than 0. The product of P and Q, which is N, is greater than M and C. So the message and the ciphertext both need to be smaller than N. And the last restraint, E and phi P times Q, are coprime. So E and phi N are coprime. And then we get to the code part. M 3200 is given to M. This is the original message. And then we print plaintext and the value of N. This is just to make sure that we have the plaintext right. And then we define P and Q as 53 and 61 and find phi, which is P minus 1 times Q minus 1. And then we print P times Q, which is N, basically. And then we print phi and the value of phi. And then we define E as 17 and D as 2753. So E is the public key and D is 2753, the private key or the secret key. So we skip the parts of how to find E and D, but we'll talk about it in later meetings. And we'll just use the numbers here. And then we print E times D divided by mod phi. So E times D divided by phi and the remainder of that. This should equal 1. If it equals 1, then we know we're getting it right. And then this line is the encryption, basically. So we encrypt using P, Q, E, and M, and that generates the ciphertext, which we put into the variable C. And then we print pow M comma E, which means M to the power of E, but as a string. And then we print the value of it. And then we print C equals and the value of C. And then after we've done all of this, the ciphertext is ready. And then this is the encryption part. And then for the decryption part, this is the line that does the encryption. So, the decryption. So we use the function decryption with P, Q, D, and C. And then that finds the M, and we give that M, which is the plaintext that we found, into the variable M found. And then we print pow CD, and then the value of C to the power of D, M found equals the value of M found. And then lastly, this if statement is to see if we did the whole thing right. If M equals M found, so if the plaintext that we found is the same as the original plaintext, then we would print M, which is the plaintext, the value of M, and then we print a string, process successful. If these two are not the same, then it prints the value that M is, which is the plaintext that it should be, and then it prints incorrect. So we can run it now. Okay. So it says plaintext 3200, so that's right. And then the second line should be the product of P and Q, so that's 3233. Phi is 3120. And then the remainder of E times D divided by phi is 1, which is right, because this is one of the restraints and it has to equal 1 in order to be right. And then here the power of M to the power of E is this big number, and then C, the ciphertext, which Alice sends to Bob, is 1380. That's the encryption part. For the decryption part, C to the power of D is in here, a very big number. And then they find the plaintext, which is 3200. And we can see that the plaintext that they found again is the same as the original plaintext. So it prints process successful. And that's the code for RSA process. RSA reliability. How secure is it? So the 6 numbers appeared are P, Q, N, Phi N, E, and D. The public key uses N and E, so everyone can know the values of N and E, and the rest are private. The most important number is D, because if D is leaked, then the private key is leaked. So can someone find D from N and E? The only way of finding D is from E times D divided by phi N has a remainder of 1. So if we know the value of phi N, then we can find D. But phi N equals P minus 1 times Q minus 1, and we can only find phi N if we know P and Q. And we can find P and Q because N equals P times Q. So if we can prime factorize N, then we can find P and Q. So conclusion, if n can be prime factorized, d can be derived, which means the private key is cracked. But in real life, the prime factorization of big integers is very difficult. Presently, no effective methods except for brute force has been discovered. So you basically run the computer for a very long time and try to find the prime factorization of it. And also, if the key is 1024 digits long, then it cannot be cracked. That's why we want the n to be really big, and that makes it the safest. So basically, RSA is really safe, and that's why a lot of people are using it right now, like our banks. Thank you.